microphone. Hello, welcome to another episode of Author Meets Physics. I'm Dave Baker. I'm here with James Reed of Oxford University. James, raise your hand so that people can tell which you are. And Niels Martens, still at University of Bonn. That's right, Niels?
Yes, for another month or so.
Yeah, and then moving on to remind me.
Utrecht, then BHI, then Utrecht, then BHI.
Ah, BHI being the Black Hole Initiative. Right, wonderful. So exciting. Okay, it's great to be here with these guys. I've been wanting to talk about this paper for a long time. I think this paper is, I mean, as with every entry in this series, it's one of my favorite recent essays in the philosophy of physics. In this case, in addition, it's an entry that kind of like speaks to a bunch of my hobby horses. So I hope that I can conduct this without being like too opinionated or hobby horsey or whatever. But the paper is Sophistry about Symmetries, which is a play on words with the title of the paper that it's replying to, which is Neil Dewar's Sophistication about Symmetry, is a really interesting piece. So welcome, you two. And yeah, I mean, great to be here with both of you. So let's kind of start out with some lay of the land stuff. I want to talk about like, what is the view of Dewars that you two are kind of replying to, objecting to, and there's a number of distinctions. There's I think maybe one way to kind of like start out is to do just a little bit of road mapping for the viewer or listener. You know, there's kind of two key distinctions that kind of like break down the two sides of this debate. So there's the sophistication versus reduction division, right? Where Dewar is more on the sophistication side and you guys are more on the reduction side. Although as we'll talk about, there are versions of what's called sophistication that you are also happy with. And then there is the interpretationalist axis, right, as you call it, and the motivationalist axis, which is a distinction that comes from the work of the great Tom Muller-Nielsen. So yeah, so I think like maybe best to kind of start out talking about sophistication and interpretation, and then we can kind of, once we got that on the table, move into, or sorry, sophistication versus reduction, then we can kind of move into interpretation versus motivation, right? But one nice thing about sophistication is that it'll be familiar to a lot of viewers, listeners, because it's related to this idea of sophisticated substantivalism, which is kind of a pretty widespread and standard view in the philosophy of physics. Okay, so like maybe the way to proceed is for me to kind of talk a bit about the way I understand sophisticated substantivalism, and then you two can kind of come in and explain what sophistication about symmetries in general is supposed to be as Neil Dewar kind of understands it, right? Mm-hmm. So sophisticated substantivalism is this kind of view that goes back to like basically the 80s, I guess, or like the early 90s or something, that kind of period when people were responding to the whole argument, understood as an attack on the substantivalists about space-time, which is to say the person who thinks that space-time structure is kind of independent of matter in some way and really exists. Details of that maybe to be filled in, but that's the idea. So the sophisticated substantivalists were folks who thought it didn't make much sense, were and are, right? I guess I count myself under that moniker of a sophisticated substantivalist, but it's a view according to which it doesn't make much sense to say that there's a difference between space-times that are related by symmetry transformations, right? Space-time symmetry transformations, that is, or isometries of the space-time, even when those things make what can kind of look mathematically maybe naively, those transformations can make a difference because they can move what's happening at like which point, right? Which point in the manifold that the space-time is kind of structured over. And so the sophisticated substantivalist view is I guess like a family of views. I think of it as being, or like a family of views, maybe with like even some details to be filled in. But the idea is, well, making a change that only amounts to a change in which point fills which role in the space-time is not a real physical change, right? We're going to adopt some metaphysical picture, and there's a variety of metaphysical pictures that might be able to do this work, but the work that is to be done is to assert that if you change which point in space-time is playing which role with respect to other points, for instance, like has which distance relations to which other points, but you don't change anything about, for example, like which distance relations hold between pairs of points kind of quantified over or something, then you haven't made a real physical change in the space-time. And you should think of these two space-times as really like identical or descriptions of the same structure. Okay. So like I mean, I hope I said that right, having held this view for many years, but anything you want to say kind of bouncing off of that, or correcting any bit of it, and then tell us a bit about what Neil Dewar has in mind when he suggests that we can take other symmetries besides space-time symmetries and talk about sophistication as an interpretation for those symmetries.
I mean, what you said sounds totally right. So maybe I'll just add that there are different kinds of transformations, and not all of them just change which points instantiate which properties. So in that category would be, as you mentioned, Hall transformations, also like static shifts in the case of Newtonian mechanics. So just displace the material content of the universe. You haven't changed any of the relational facts about the material content of the universe. You just change where material content is located. So those are symmetries of the kind that you mentioned, and I think this is going to be important later, not all symmetry transformations are of that kind. So other things like the kinematic shift, which I think we'll talk about more, where you boost the material content of the universe, is not just changing which points instantiate which properties. And as traditionally conceived, sophisticated substantivalism is targeting just the former category of symmetries, saying when it looks like you have two distinct possible worlds, but they differ only with respect to which points instantiate which properties, you should be a sophisticated substantivalist and think that in fact those don't represent distinct physical states of affairs. And as you mentioned, Dave, there are lots of different ways that you could go there. One would be to reject the idea of hexaetistic properties like trans-world identities of space-time points, to say, well, the center of mass of the universe is at point P over here and not at point P over there. Well, if I scrub out the labels, you can't really articulate the difference anymore. So that would be like one way of being a sophisticated substantivalist. But just to add really that these traditional debates, which as you mentioned, go back to the 80s, are really focusing that like former category of symmetry transformations.
Mm-hmm. Yes, and then so in our paper we call this traditional sophistication, and then Neil Dewar has two additional versions of sophistication, right? Internal and external. And I think it took us a while to realize that it's very easy if you read the paper to think that the internal one might be a specific instance of external sophistication. I think it's important, as you try to point out in our paper, that they're not. They're rather two different ways of generalizing traditional sophistication. And so in the internal case, what you're going to do is to find a way to semantically reformulate the theory, right? So you don't change what Neil Dewar calls the syntax, the equations, but you only change the models such that they reach the right form, where then you can just make the traditional sophistication move where you forget about quiddities or forget about hexaeties, depending on whether you're talking about entities or properties.
An example might help here, I feel to kind of illustrate for the viewer, like what would kind of like what would like a concrete case of internal sophistication be?
which example shall we go for?
So basically with the internal sophisticationist move, you want to, when you have models or solutions of your theory which are of that second kind of symmetry which I mentioned, which differ more, it seems where you have models of a theory which seem to represent possible worlds which differ more than just with respect to which points instantiate which properties. What you want to do is you want to forget about the structure which generated that additional difference. So in the case of like the kinematic shift in Newtonian mechanics, where I have one situation in which the material content of the universe, the center of mass of it, say, is at rest with respect to Newtonian absolute space, another where it's moving uniformly with respect to Newtonian absolute space. That would be the kind of case that we're interested in. What the internal sophisticationist would do there would be to say, well, forget about the structure which like generated that difference, which in this case is like Newton's idea of the persisting points of absolute space, that kind of background structure which lets you articulate this difference. That's step one of internal sophistication. And then step two is, again, be an anti-Hexiatist or anti-quidditist, or however you want to implement your like traditional sophisticationist story. That's like internal sophistication, which first of all involves forgetting certain structure, and second of all, like doing the moves which are familiar from the traditional debate. That's in contrast with what Niels mentioned of external sophistication, which is kind of like the cheaper attitude, where you just assume these models, which are in fact not differing with respect to just where stuff is located, are in fact like the first kind of case of symmetries, and then apply the traditional move. So just kind of like assumes you can do the first step without actually doing it, and then applies the traditional move. And just for what it's worth, kind of anticipating our own views, or at least I don't know if I think we agree. I actually think internal sophistication is okay. I have more of a problem with the external one.
Yeah, the paper makes clear that you're in favor of internal sophistication, it seems like. Niels?
Yes, indeed. I mean, this also connects a bit to what we're going to get to when it comes to the invitational versus the motivational distinction. So I guess maybe we like internal sophistication, or we think it's a useful tool besides reduction, which can be used in many cases. And in some cases, internal sophistication does away with some problems that reduction has in those cases. But the main thing is, and we're going to get to this, I imagine, in a second, that if you connect this with the other big distinction, invitational versus motivational approach, then the point is not so much the sophistication, reduction, whatever, but that you are guaranteed that it always works. And whereas we think internal sophistication is a tool which might well work in certain cases, to then connect this to the other debate, the other distinction, which we're going to get to, it's important to say this works universally. And we don't think there's a good reason, at least not a priori or in any obvious way, why internal sophistication will always work. And then Neil Dewar will say, oh, but then we use external sophistication. That's a trick you can always do. And if that were true, I think that would indeed then support the internal interpretational move. But there we think, as James said, that's more of the, whereas we like internal sophistication because there's actually non-trivial work being done. The external one seems a bit more of a cheap move, but you declare that models that are not isomorphic are as if they're isomorphic, and then you follow that up with the traditional sophistication move. And we're not sure that that move really is an honest form of realism, that it comes with a transparent picture of the metaphysics that we're trying to. I think there's.
Oh, go ahead.
Sorry. I was just going to say maybe there's quite a lot of jargon floating around. So can I try and like at least synthesize it a bit?
Absolutely.
So just to recap, so traditional sophistication is the view that occurs when you have symmetry-related solutions of a theory which differ, which seem to represent possible worlds which differ merely with respect to which space-time points instantiate which properties. And you can be a sophisticationist by, for example, being an anti-Hexiatist and not thinking that space-time points have primitive trans-world identities. Now, then you get the case of symmetry transformations which seem to represent possible worlds which differ more than merely with respect to which points instantiate which properties, like the kinematic shift. There are lots of other examples like gauge transformations in electromagnetism, blah, 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 blah. We can talk about loads of them. Then you have the option of being an internal sophisticationist or an external sophisticationist. The internal sophistication strategy, A, forgets about structure, and B, applies the traditional sophisticationist move. What you're doing there is you're keeping the same number of solutions, but by forgetting about structure, you're kind of placing yourself explicitly in the first kind of case again. You have the same number of solutions, but now the solutions, to use the term that Niels mentioned and we'll come back to, are now isomorphic, and then you can apply the traditional sophisticationist move. The external sophisticationist says that you just can do that, but doesn't actually do the work, and then says, then apply traditional sophistication. This is to be, both of these strategies to be contrasted with reduction, which is a term which Niels mentioned, which is where you actually change the number of models. So you have a whole class of symmetry-related models of your original theory, which might differ by kinematic shifts in Newtonian mechanics or gauge transformations in electromagnetism or whatever. And you map all of those to one solution / model of your new theory. I actually think this is kind of cool. So you don't just like forget about structure to make the solutions isomorphic, but keep the same number. You actually like change the number of solutions. And I think the most straightforward illustration of the difference here, and we can talk about this more if people want, is actually in the case of electromagnetism rather in the case of these space-time shifts that we've been talking about.
Yeah.
So there you have your standard gauge transformation where you can take A to your electromagnetic 4-vector potential to that plus a gradient term. And so that's a symmetry. If I have a whole class of symmetry related models which differ by this gauge transformation, the reductionist move maps all of those solutions directly onto what's called the Faraday tensor formalism of electromagnetism. So you have this object, the Faraday tensor, which directly encodes the electric and magnetic fields without this gauge freedom. And so you kind of just like have this whole class of solutions of your 4-vector potential formalism of electromagnetism, which map to this single solution of the Faraday tensor formalism. That's to be contrasted with the internal sophisticationist move, which, and we can talk about this more, here you get into some like complicated maths, but ends up being like the fiber bundle formulation of electromagnetism, which retains the same number of solutions, but which renders the solutions isomorphic. And actually, Neil talked about this a little bit in his paper. There's also a nice discussion elsewhere, like in Caspar Jacobs' thesis and stuff. And I think then you can like directly compare whether reduced theories are better or worse than internally sophisticated theories. In both cases, you've given a story about how these symmetry-related models represent, in fact, should be regarded as representing the same physical state of affairs, but it's different because in the reduction case, in this case, you believe in a Faraday tensor. In the electromagnetism case, if you internally sophisticate, you'd believe in like fiber bundle theoretic version of electromagnetism, whatever that amounts to. There are like conceptual and technical reasons to often prefer the internal sophisticationist route. Like just as a simple example, you don't have nice action principles for the Faraday tensor formalism of electromagnetism. So
right,
yeah.
Right.
Anyway, sorry, that was like a long. But I hope.
No, it was very clarifying though, just as you intended, I think. So as far as external sophistication, which is I think especially important because that's the kind of part of the view that Dewar asserts that you disagree with, kind of like on the whole in principle, you don't like it, period, right? It's interesting. One of the things that you point out in your paper, and I had the same feeling once I went through your explanations of it. One of the things you say in the paper is that the examples of sophistication that Dewar gives that are kind of clearly spelled out are really all examples of internal sophistication, right? And that it's not clear that he kind of gives an uncontroversial example of external sophistication. Yeah, go. Sorry. Well, okay. So the kind of thing I was thinking was like, one of the things I was thinking here was like, what would really count as a kind of happy example of truly external sophistication, right? I mean, I guess one thing, maybe the clearest way to give an example would be to use the kind of example you were just talking about, and say something like suppose so you gave the example of the fiber bundle formulation of electricity and magnetism, where like you come up with a version of the formalism where there are isomorphisms of this geometric structure, the fiber bundle, between all the solutions that are related by gauge transformations, right? So there was a point in the history, perhaps, of electromagnetism, there was, when we didn't have that formalism, right? It hadn't been come up with yet. So perhaps external sophistication would be the view that if I just have the theory written in terms of the vector potential, I present that theory and I just say I'm counting states that are related by gauge transformations as physically equivalent, and leave it at that without constructing the further the further structure where gauge transformations are represented by isomorphisms, right? And I mean, I think that one thing to say about that move is that it's kind of a move that you see physicists make sometimes, right? Like it kind of seems like something that people do. So this is getting fairly far in the paper in terms of page count, but I think dialectically it would be a useful moment to kind of say, like, what's uncool about that move according to the two of you.
I think it's totally cool from the point of view of physics practice to say I'm treating states which are related by a gauge transformation as being representing the same physical state of affairs, but maybe physicists aren't always interested in giving metaphysically perspicuous characterizations of their ontological commitments. And I think to simply say that doesn't give you everything that a metaphysician or a philosopher of physics might be interested in. At least it doesn't give me everything that I feel like I'm interested in. An analogy comes to mind, but it literally just came to my mind, so I don't know if it's actually going to be fruitful or not. So consider the difference between like constructive mathematics versus people that are willing to help themselves to proofs by contradiction. And it's one thing to say like, oh, these models are empirically equivalent, but if I were to treat them as representing distinct physical state of affairs, that would be problematic somehow. So in fact, I'll regard them as representing the same physical state of affairs. That's like your kind of like normal maths like approach, but I'm kind of more interested in like, I want to give the construction which illuminates how these things represent the same physical state of affairs.
Mm-hmm.
Anyway, it's the thing.
Yeah, so indeed, my worry would be when you say physicists do this all the time, then my question is for which purpose? If they're just being pragmatic, right? If they're just trying to do calculations or apply the theory, then I can totally understand, yeah, that's all you want to do. But what, at least in our paper, we take to be the terms of the game, what we think Neil Dewar agrees on, that we're trying to be realists here. We're trying to say, if this is formalism, which metaphysical picture of the world goes with that? We actually have talked with Neil Dewar about, is this really a form of realism, etc. But I think in our paper, we assume, as we think he does in his paper, that we're trying to be realists here. So then the question is, right, if we switch to the example of kinematic shifts, right? If in some of these models, it seems like the center of mass of the universe is at rest with respect to absolute space, and in others it's not. That's a very clear, qualitative, understandable distinction about the world. And then if you then say, well, these are physically equivalent representations of the world, the world is whatever structure they have in common. I'm like, well, they very clearly make a distinct claim about the world. What does it mean to say, forget about that difference? Like the theory cannot talk about, right? Everything in the theory kind of builds up on, right? Relative velocities depend on absolute velocities. So to then say, well, we're just going to ignore that part, that seems to, I'm not sure why that's a form of realism. Of course, if you say, well, we're not interested in realism, anti-realism, we're just doing the calculations using the theory in a pragmatic way, sure. Then I don't have anything to say against that. But I take that, at least in the paper, Neil Dewar nor we are trying to do that.
Yeah, right. So it's important to the dialectic here that both sides of the debate are trying to give a, we might say, kind of like fully satisfying and explanatory terms picture of what sort of underlying reality might explain the success of a theory, which isn't as you allude to, kind of like always what physicists themselves are in the business of doing. Yeah, good. I mean, I guess let me run something by you and see if this sounds like the kind of principle that's in play here, right? So like for example, if somebody came around and said, hey, like I've got the following theory, like, there's a cat, the cat is on the mat, right? Pretty great theory, but like now take on board the empirical consequences of that theory, perhaps, but just erase everything I said about animals, right? There are no animals according to everything I just said, or something like that. Well, you might say like, what I just said is kind of like an incoherent combination or something, right? Like I can try to deny some of the metaphysical implications of the theory I put forward, but I'm not going to be able to succeed at that in kind of a coherent way, right? Like the theory, if you try to subtract some of its ontological commitments, the theory becomes incoherent in a particular way, right? And so like so when I've you use the term, I think James used it, metaphysically perspicuous, which is a term that comes from Muller-Nielsen, who is kind of the kind of like original source for a lot of the viewpoint that the kind of general approach, at least, that you two are taking. And a thing that I have at a few times tried to understand about Muller-Nielsen is like, what does metaphysically perspicuous mean? So as kind of like, I mean, I know you guys like are like have talked a lot with Muller-Nielsen about this stuff, and of course are like advancing the view in your own right. Like, if I could just ask, like, is this the kind of thing you have in mind? Like that what you need is maybe the way I'll put it is like an explanation for how it could be like coherent to say that the things the theory is saying about ontology are true, and also the things that you're trying to say the theory isn't saying about ontology, right? Like that, you can kind of like combine the positive commitments that the theory has with the statements about physical equivalence that you're trying to make in a coherent way.
Yeah, that sounds completely right to me. And I found your cat examples actually be really a good one here. So
yeah,
that, giving the line of argument that you gave from the cat example, that's definitely not metaphysically perspicuous to me. So
yes, that is the heart and soul of metaphysical perspicuity. Cool. Yeah. Okay. So this is good. So like, so let me grill you a bit about this concept as it gets used in your essay, right? Because so as you've kind of obliquely alluded to in the discussion so far, you're on board with something that Muller-Nielsen is also on board with, and that Dewar is also on board with, which is that there's like nothing wrong whatsoever with traditional sophistication. There are folks out there, my main man Shamik Dasgupta being one of them, right, who would question this and say, well, no, like traditional sophistication is also problematic in the sense that you are worried about, in the sense of metaphysical perspicuity, because you, in the case of traditional sophistication, what you're saying is, well, look, there are all these space-time points, and like now I'm identifying solutions or models of the theory that are related by symmetries. So I'm kind of forgetting which space-time point is which, among other things, when I do that. And what I think Shamik would say is, well, that's not metaphysically perspicuous because you've told me that there are these points, and like, yet you have said something which seems to contradict the idea that there are these points, which is that there's no fact of the matter about you know, which point this one is, or something like that, right? Or maybe another way to put this that's a little more in line with kind of the way that we're framing this is, like if you write up the formalism, one of the things that the formalism includes is a manifold, right? And the manifold has points, and for any solution, there's a fact of the matter about which points are playing which roles, right, in that solution. And the way you have of putting the theory forward is to put it forward in terms of these solutions, which say things about which points in the manifold are playing which roles. So I think what Dasgupta would say is, well, you don't have a metaphysically perspicuous description of the physics you're talking about until you have a description where you're saying just the things that you think are real and none of the things that you think aren't real, right? And you don't have that in the case of, like, for example, like a solution of ordinary general relativity, because it does talk about points and what the points are doing. And like, yeah, you can talk about equivalence classes of those solutions, but, you know, then you're kind of doing, again, Dasgupta would say, the same kind of thing that you're accusing Dewar of doing.
So I could say things if you want to. So, I mean, the way that things like the static shift or pole shifts initially look like problems is that you have manifold points and they have instantiate certain field values, but you also think that those points have certain, what metaphysicians would call impure properties, hexaeties, have certain names attached to them. And it's by thinking that they have both that you generate the problem, because then you say, like, P has this field value in this possible world, P has a different field value in some other possible world. Seems to me perfectly metaphysically perspicuous to say, well, I don't believe in impure properties, I scrub them out. That seems to me, I can still understand what's left. I'm saying only the things that I believe to be true. There are points, there still exist points. That's a key thesis of sophisticated substantivalism. They still have certain field values, but they don't have names attached to them. So, and by saying that, I no longer regard these distinct models of my theory, whether it's general relativity in the case of the whole diffeomorphisms or it's Newtonian mechanics in the case of static shifts, as representing distinct physical state of affairs, as representing distinct metaphysical scenarios. So it seems to me like I have given you like a metaphysical story about what's going on. I've purged my points of certain things which I found to be problematic, but I still believe in the points and I still believe that they have other properties, the ones I believe to be non-pathological. But I don't know what Dasgupta would say in response to that. I don't know if you agree with what I just said, Niels, but
yeah, I think so. So what intuition that seems well, Shamik in Dasgupta seems to have an intuition that differs from the one we seem to be having, is that when I think of a point, right, which you could, right, which Goto could then use to build a manifold or build something else, like the most simple instantiation of a point is that it doesn't have a label, right? It doesn't have a primitive distance. It's just a point, right? It's just something which has no extension. That's all there is to it. And then it seems to me like, well, you could add more structure to this, namely give it a name. And then, but the question that people like Shanita often ask is, no, but the most basic way of talking about points is with a label, and then tell me how you get rid of it. But I mean, that's already the wrong starting point, like the simplest way, right? So I don't know if the following metaphor is going to be useful or not at all, right? But so one way of thinking about it is that you have a metaphorical God with a bag of points, and he's going to create one model, putting all the points next to each other, having space-temporal relations between them, and then say, okay, now I'm going to put them all back in the bag, and then going to create another model with the same points, right? And what then Shamik might be thinking is like, oh, well, but if you use kind of the same points, then even if you put them back in the bag, you can still say which, when you then create your second model, right, or second possible world, you can still say, oh, well, the point that I used here on this spot, so let's say the point I put at the center of the Earth, there's a matter of fact as to which point that was when I built the first model. But then, of course, that's only the case if you kind of, right, this God lives in an overarching larger space in which you can say, well, he took this point, but that's not the case. If you have different possible worlds, they don't stand in any spatial temporal relation whatsoever. You can't, like, the default position is to not think there's any way of saying, well, this is the same point, right? The most simple way of thinking of a point is that it doesn't have these labels. And even if you think, okay, maybe the default way of thinking is that they do have these labels, then it's still very easy to get rid of them because there's no qualitative aspect to it. It's just a name, it's just a label, right? What we have problems with is where there are cases where there's lots of structure, complex structure, and you want to get rid of part of it and not the other part, and it's not at all clear how you disentangle that, right? So if you want to say, if you have a theory like Newtonian mechanics and Newtonian spacetime, where relative velocities are defined in terms of absolute velocities, right? Then I don't know how you can say, oh yeah, I like relative velocities, but not the things in terms of which they're defined. Whereas when it comes to just non-qualitative labels, it seems like you can always disentangle that. It's just a name. You can say, okay, forget about the name. It doesn't have any effect on the structure because it is non-qualitative. Okay, let me stop there.
Sorry, can I say one other thing, Dave?
Yeah, absolutely.
So the way that you presented traditional sophistication at the start was something like, when I have models which seem to represent worlds in which differ only with respect to which points instantiate which properties, then I should in fact treat those models as representing the same possible world, the same physical state of affairs. And that has the flavor of external sophistication to it, I agree. But I think it's pretty easy to give the like internal sophistication parallel of it, which is just purge the hexaeties.
Well, yeah, okay, so it's interesting, right? So I mean, in a way, some of these questions kind of butt up against the foundations of logic in the sense of like you know, one can ask kind of a question about like whether it's satisfactory to put forward a theory that, you know, in which like proper names are kind of like how to put it, like a theory in which it's incoherent to use proper names to refer to the objects in some sense. Like you're not allowed to like talk about you're not allowed to name the objects that are in the domain, right? That's kind of it sounds to me like that's kind of like, in a way, what you guys are suggesting would be a more accurate kind of like picture of how we would talk about space-time points, right? That they're the sort of things that can be quantified over, but can't be, or like you would quickly run into like mistaken or misleading theorems if you allowed yourself to talk about names for those things in some sense, right?
I mean, I wouldn't say not allowed. I would say you're allowed not to do that, right? I mean, you can give these names. We're just saying, and we're not saying Shani cannot do that. We just think he cannot tell us that we have to. And it's
good. Yeah. So like I was thinking like the view is that like real world space. So like in principle, there could be space-time points in like a different theory other than, you know, like a space-time theory the way that you want to interpret it. But like in a space-time theory the way you want to interpret it, right? The only way that we can think in a sense about names for points would be in terms of like definite descriptions or something. If that makes sense. Like I guess a way to put this is I think in the terms that the metaphysicians like to use, the foundations you're suggesting for sophistication would be something like what they call quantifier generalism, where you say that like the basic facts about I'll put it this way. You could write up the theory in terms of just existentially quantified statements and not leave out anything that's important to the theory, or that's like that the theory is saying is real in some sense, right? Like does that sound appealing?
I think so, but maybe to just, but she said, right, in different theories it might be different. And you could say if you have a theory, an Aristotelian theory, then you would, right? So then it would be different. So that's why we're not saying you're not allowed to, right? Sometimes you actually have to in the case of Aristotelian spacetime, Aristotelian physics, but I think generically you should also be allowed not to use these proper names. And in the case of, say, Newtonian gravity, there is no adding this structure that's not needed and not necessary. And yeah.
Right. So like the correct interpretation of Newtonian gravity could be one that could be stated just quantificationally without talking about names for points or yeah. Right. Good. Yeah. Yeah. I mean, I think I agree with that. Like so the I think that like the kind of thing that um the opponents of this would say is something like, well, um existentials have to be grounded in their instances, right? You know, it has like it's never the case that there exists an F except because, you know, some individual is an F, right? Like call that individual Bob, like Bob is F, right? That's kind of, so that's the kind of thing that and I think this is one of the big cleavages in like where people's intuitions or background commitments are between like physicsy people and like metaphysicsy people, right? Like I don't know if you guys feel this way, but like for me, you know, I grew up on people saying, hey, in quantum mechanics, the particles, like there's no fact of the matter about which electron is where in the state, you know, like switching the electrons in the state doesn't do anything. And it just kind of became very like natural for me to say, yeah, like there are electrons and there's no fact of the matter about which electron plays which role or something like that. And I just kind of like drank that Kool-Aid. But people who haven't drunk that Kool-Aid and kind of like get deep into metaphysics, I think have more the kind of commitment that like you're saying something incoherent really when you say that something exists without it being any particular thing or something like that, right?
But we're not really saying, I mean, we're not saying there are points. It's just that we don't believe that these points have certain hexiatistic properties which underwrites a notion of transworld identity, which generates the particular metaphysical issues at play. So
yeah,
I think what you were just saying does two things at once. Right? So you're saying, well, you cannot have this existential, these statements with existential quantifier without having an instance that grounds those statements, right? But then you snuck in saying, so there needs to be something with a proper name that is that, instantiating that thing. And that's kind of a second step. So we're not denying, yes, if we talk about a space-time, a sophisticated space-time, there exist points which send in such and such relationship to each other. Yes, for that to be true, there must indeed be individual points, right, which instantiate that. We're saying, here they are, I can point at it. I just refuse to say that I need to call that point by its name for it to be the case that it's indeed instantiating thing. Right? Yeah. Instead, I can say, come here, Dave. I'll point you at it. I refuse to say like the only way I'm allowed to make you acquainted with the point is by giving its name. So yeah, that's the part where we go, or not that there are no instances.
Good.
Yeah, okay. Then that will be a problem for a few. But
yeah, right. I think I was speaking. Yeah, I think I was speaking imprecisely when I said that part of what I just said. Good. Yeah, cool stuff. Okay, so let's get to the motivational versus the interpretational views of symmetries, right? So Dewar is an interpretationalist. You two, together with Muller-Nielsen, are motivationalists, right? So like yeah, I feel like it would make the most sense for you to kind of lay out like, you know, what's the difference in these two views, right?
Yes, so so Tom Muller-Nielsen did a great job at making explicit the difference between the received view and an alternative view that the three of us favor. So the interpretational approach to symmetry, sometimes interpretationalism for short, is the received view, and that's the idea that as soon as you have a theory with symmetries, you can typically always invariably universally say, okay, we know these models related by symmetry are just a difference in representation. They always represent the same possible world, the same physical state of affairs.
Just quick point of order. So like by a symmetry, you know, some people will kind of say like, you mean a symmetry, like you mean something that's like like a transformation that preserves the dynamical laws and the empirical content. That's kind of like,
that's in all of these debates and in all of these papers, that's what people have in mind. And there's kind of related debate about what the right definition of symmetry is. Do you want to cook in empirical equivalence into your definition, like that's what it does? Or do you just want to think about some other definition of symmetries and then restrict yourself to the ones which actually are such that symmetry-related models are empirically equivalent? I think in this interpretationalism, motivationalism, sophistication, reduction debates, we're just assuming that the symmetry-related models preserve empirical content, and we're thinking about what to do with models of your theory like that.
good.
Yeah. So either one can just define symmetries that way, or you could say in this paper we're only talking about symmetries which happen to also be such that they relate empirically indistinguishable.
Yeah. Great. Okay, sorry, go on, Niels.
Yes. So then the alternative to this received view is the motivational approach, which says, okay, if you have a theory, a physical theory with symmetries, that's great. That gives us a hint that maybe we can do better. It motivates us to find a theory that's sparser, more, right, has less structure. So it says, okay, that means we should try to find a theory that does away with the this plurality of models for one physically possible world. And then you might do that via reduction. You might do that via sophistication. The point is, only once you have actually found a reduced theory or a sophisticated theory, then can you say, so as a matter of epistemic humility, only then can you say, okay, now we have justification for saying these models in original theory related by symmetry are indeed representing the same state of affairs. They indeed are only a difference in representation. But until that point, because we think it's not guaranteed that you can always find such a sparse, such a reduced theory or sophisticated theory, that's often involves highly non-trivial mathematical feats. So we're like, well, until that point, you kind of should remain agnostic or cannot yet make the claim that symmetry-related models of original theory represent the same physically possible world.
Yes, cool. So like, it doesn't seem like a coincidence that the sophistication approach and the interpretational view are married in one man, Neil Dewar, and that the motivational approach and the kind of like at least opposition to external sophistication kind of come together in your point of view. Like, what is it that makes, I mean, maybe like kind of concretely, what is it that makes the interpretational view and the external sophistication view such natural partners? Like, why does, you know, because like, I think it's true that like Dewar has good reason to assume them both together. Why is that?
Yeah, so I'm not totally sure they are natural partners, right? So indeed, well, depends on which type of sophistication you mean. So correct me if I'm wrong. So Moller Nielsen basically says, well, only in the cases where it's already isomorphic, like sophisticated substylism, their sophistication is okay. In all the other cases, we're doing reduction. We actually think sophistication is a tool that works in many other cases, at least when it's internal sophistication. But the whole point, if you want to justify interpretationalism, right? If you're saying we don't want to do the work of finding a reformulation of a theory before we draw the metaphysical conclusion that symmetry-related models represent the same state of affairs, right? Then basically you need to have some reason to say, well, we don't need to do the work. There's a tool that's always going to work. It's kind of a priori, right? Whether you think reduction is always going to work, whether you think sophistication is going to work, and then the move that Neil Dewar makes is says, well, when we go to the specifically the external variant of sophistication, he thinks, right, because you just, even if models are not isomorphic, you just declare that they're isomorphic and then apply the traditional sophistication move. So it's this promise that this tool can apply universally, which can then be used to support interpretationalism. So if you just take the tools by themselves, like internal sophistication. We like that tool and think you can pair it with either view. It's all about the promise that the tool applies universally. And I'm not sure if I don't think anyone would say, well, reduction it's guaranteed that's always going to work. So you don't even need to show the reduced theory that's always going to work. And then Niels Duer thinks, well, in the case of sophistication, maybe you can make that move, at least when you use external. Yeah. So I guess, okay, in that sense, when it's about the universal application of external sophistication, you're right, then it naturally pairs with interpretationalism. If you use the tools and other variants, then you can pair it with both approaches. Right.
So if Duer didn't think that external sophistication worked, let me put it this way, right, and see if this is if this sounds right to you. If Duer didn't think that external sophistication worked, then he wouldn't be licensed in being an interpretationalist, because he might run into a theory where there's no obvious reduction for it, and internal sophistication doesn't work because the symmetry related states aren't related by isomorphisms of the theory's math, right? And yet he's supposed to think that he's in a position to believe that this theory, that the states related by symmetries of this theory are physically equivalent. If you can't do it by internal sophistication, you can't do it by traditional sophistication, then you got to do it by external sophistication.
Yeah.
Right.
Yeah, I mean, that's right. So for me, there are two steps in constructing a reduced theory or an internally sophisticated theory. Let's just focus on internal sophistication. So one is to actually construct the new mathematics according to which your models are now isomorphic. And in the case of the fiber bundle formalism of electromagnetism as an illustration, that's non-trivial. And you also need to interpret that, do some metaphysical work. And even if you can give an argument to the effect that you could always construct some new mathematics where you've purged all of your variant structure and somehow realize the ambition of having isomorphic models, it's not obvious to me that you can make the second move. And I think this becomes, my reason for thinking that becomes clearer when you think about weirder and weirder symmetries, or maybe in the case of dualities, which is something that Tom and Niels and I talked about a little bit in one of our papers in this series as well. You can have really complicated symmetries relating seemingly really different models. And if I construct an internally sophisticated theory, it might be using some super highbrow category theory or really fancy maths. And even if I had that, I wouldn't necessarily be sure I could interpret it. So yeah.
Right. There might be a kind of, right. It might be that sophistication was possible in some formal sense, but you don't have a clear physical picture of what the theory is saying.
Yeah. So even if Neil could argue that well, actually, here's an argument to the effect that internal sophistication is always invariably available, I'm still not sure I would be convinced if that were just a mathematical argument, because I think there's also metaphysical or philosophical work which needs to be done.
Good. Yeah, interesting. I mean, so excuse me, I have this quote. I did warn you guys I was going to ask you about this quote. But I have this quote from the paper that I wanted to ask about, because it's a quote where I'm wondering whether it's one that you might want to walk back a little bit in terms of is it making out the motivationalist view to be pretty radical, right? So you say this is at the end of section 2.3 on the paper for those who are following along, which you should be, because the paper is great. I meant to say it at the start of this, I forgot, but I always try to encourage viewers to read the papers or take a look at them before going over these discussions, because these discussions are me asking the things that I'm interested in asking about after I've already read the paper. So you say interpretationalists of all stripes maintain that one's regarding symmetry related models of a given theory as being physically equivalent need not wait upon an explication of the common ontology thought to interpret the physical equivalence. It's this point which crucially separates the interpretationalist from the motivationalist. So what I take from this is that the motivationalist thinks you do need to wait for an explication of the ontology. That is what you were, what we were talking about before, like a perspicuous presentation of the real ontology that you do believe in and nothing else, right? In order to be justified in believing that two solutions are physically equivalent. And I mean, I guess like one of the things that I kind of wonder about this is whether there might be examples where you could have grounds for supposing, like, I mean, take the example we were talking about before, electrodynamics, right? There was a time when we just had a version of it that talked about the potential, and like, yeah, the fields, but maybe we didn't have a version of it that was a fiber bundle, for example, right? But one might have had an inkling that a fiber bundle formalism, like a fiber bundle version of the theory, was possible, right? Like one might have, like maybe it was a conjecture, maybe it had the status of a conjecture, or maybe like like a thing that Dewar does say about Newton, which sounds kind of hardcore in a way, is that Newton maybe should have known not to be a realist about absolute space, right? Because like, does absolute space, or like absolute rest, let's put it this way, right? Does a state of absolute rest really play an explanatory role in Newton's theory? Well, nowadays we can kind of see that like it doesn't play an indispensable role in the theory, right? So of course Newton didn't have a construction of like Galilean space-time in front of him to show that the absolute rest was dispensable. But a thing he might have thought of is like, like conjecture. Somebody could construct a space-time that does away with absolute rest. Like, I'm fairly confident that that's possible, one might say, in Newton's position. So I'm fairly confident that solutions related by boosts in Newtonian mechanics are should be understood as physically equivalent, right? Like, does the motivationalist say no, you can't do that?
I have a very long answer, so if you have a short
my short answer, like, I think I'm fine with with conjectures like that, but the proof's in the pudding, and I would only want to say, yeah, these actually do represent the same physical state of affairs when I've actually seen the construction. It's like, I can be pretty confident about it, but I would only want to make the definite statement when I've seen the hard work made good on.
Mm-hmm.
That's short answer. What's your
long answer from Niels? Yes.
Okay. Yeah. So, well, this relates to a debate I had recently with Tushar Menon, who was the first speaker, I think, in the series, right? And that had to do with, well, basically Occam's razor, which I think is something that doesn't really get talked about enough. What's kind of in the background here is often the idea like, oh, some version of Occam's razor, whether that's the invariance principle or the principle of sufficient reason or PII, you have all the different ones, but it basically boils down to some version of Occam's razor, right? That we shouldn't multiply entities beyond necessity, or shouldn't have more structure than needed, etc. And I always think, okay, this is what you learn in the first year, and everyone goes along with it. But I think the question asked is, well, okay, what kind of beast is Occam's razor? Is it supposed to be some absolute truth? Because sometimes it's treated as, yeah, the world cannot be such that it has entities that we don't need or don't observe, which seems highly anthropocentric. So I don't think, yeah, so I'm worried that often it gets mistaken for some absolute truth. And I think the mistake that's made there is that we go from absence of evidence for some structure, entity, quantity to, oh, that's evidence for the absence. And well, I mean, that's not logic, that doesn't follow logically. And unless we go like hardcore logical positivist and we think, well, it's meaningless to talk about structure, like absolute velocities that we can't see. But I think most people in the modern debates don't take that route. So I'm assuming that's not what we're gonna go for. So then there's no logical, right? If you would have it, if you have Galilean space and Newtonian space-time, I don't think people in the modern debate are like, oh, well, absolute velocities are meaningless or ill-defined, or there's any logical problem with them, right? So it's just coherent that it's logically possible metaphysically possible, that the world is such that it has structure that we can't observe, etc. Right? Another problem with that is also that when we talk about evidence, we tend to equate it with this observability, where there can be other evidence, right? In the case, it can just be that you need something to explain the observable stuff, even if that stuff itself is not directly observable. So, for instance, in the case of, again, relative velocities, in the standard picture that Newton had, yeah, you needed absolute velocities to explain relative ones. So there was evidence for absolute velocities as well as relative velocities. So what I think this all leads to is, so Occam's razor can be an absolute truth. It is more an methodological principle of epistemic humility, which doesn't say, oh, if we have redundant structure in a way that we can clearly excise, right? Then we definitely know this doesn't exist. It's more like the question is, okay, which structure are we certain, or certain-ish, that exists? So that's kind of the question we're asking. For which structure do we have enough epistemic, enough justification for believing that it exists? And then we need to be agnostic about the other parts if these can be clearly separated. Now, if you have only one theory on the table, I don't think Occam's razor is going to apply there at all. If you have only one package to choose from, that's your only empirically adequate theory, which Newton's theory was at the time. And if that is the only package you have, it's empirically adequate, and you need absolute velocities, absolute velocities, then I think we are very well justified in going for that. Occam's razor only works if you have two theories and say all other things are equal, which is often not even the case. All the things equal, you have two theories, and they basically postulate the same structure, but one postulates more structure, which can be cleanly cut off. Then sure, then, I mean, it could still be actually that the theory which has the extra structure is the world could just be like that, right? There's no logical problem there. But then as a matter of epistemic humility, you can say, okay, let's just only commit to the structure that we need, and this be agnostic or about that structure, right? So basically, to end with, then this comes back to what James said. He said, hey, maybe Newton should have conjectured that, right, he could get rid of it. But it took, what, 250 years before, I don't know exactly when Galilean space time. So, I mean, if that conjecture wouldn't be made, that sounds very, even in retrospect, quite bold, because it was, right, it was not that trivial to come up with it. So in more complicated cases, right, we talked about the case of the fiber bundle formulation of electromagnetism. I mean, really, if you just start with the Faraday tensor of the effective potential, are we really like, oh, surely there must be something fiber bundle? That doesn't seem guaranteed to me at all in all cases, or in any serious case.
Yeah, good. Oh, sorry, go ahead.
So I completely agree with it. It's super clear, but just to add, so some of the stuff you were saying about Newton at the end, I think is also very nicely put in print in Dasgupta's BJPS article on symmetry. So we might disagree with Dasgupta about some things, and we already saw that in the case of like sophisticated substantivalism and so on. But one of the points on which we actually agree with Dasgupta is he's also a motivationalist and gives the same kind of arguments.
Yeah, although actually it's funny because I talked to him a couple of years ago. I think it was right before the pandemic. I can't remember if it was right before or right after the pandemic. I think it was right before the pandemic. He seemed a little inclined to walk back that part of his view, actually, but he's had this kind of pragmatist turn, right? So it's like, maybe that's kind of, I think it's kind of part of that. But yeah, like, okay, so I think it's completely fair what you're saying, Niels, that the epistemology of conjectures could be tough, and like, we might, like, it might be easy to overestimate how justified we could be in accepting a conjecture, right? And yeah, like, I guess yeah, I mean, I think it's, Newton, one of the smartest guys in history, it seems pretty arrogant to second guess the guy, right? But I mean, I guess the kind of thing that motivates me here a little bit, so to speak, no pun intended, is like so the following seems kind of plausible to me, that we might end up with a theory that is really successful. I mean, I guess I'm kind of like inducting on the history of high energy particle physics here a bit, but it seems like we could end up with a theory, like a theory that's super predictively successful and kind of like explanatorily successful in a certain way, but where like we don't have an existence proof for models of it, you know, like that's where quantum electrodynamics and quantum chromodynamics are right now. And like maybe in 200 years M theory ends up in a similar place where like, yeah, boy, if it exists, this theory like explains everything. But like, we just don't have we just don't have a construction, right? We just haven't constructed models of the theory's axioms. We're not 100% sure that the axioms are all fully coherent with, like, consistent with each other, but we think that probably you could kind of like restrict some of them in various ways so that they could be made consistent with each other, and you could construct models. But like, it's a tough enough problem that like in the case of constructing Galilean space-time, it might take hundreds of years or something. I guess my intuition is, in a case like that, like, for example, suppose that a theory like that, if it exists, is going to say that certain states that aren't equivalent in like the standard model are equivalent in like this final theory of everything that we don't have a construction of yet. It seems to me like in a case like that, we could be justified in saying, yeah, like, we believe that such states are equivalent, even though we don't have a construction of models for the theory that says they're equivalent, because we think that's just a hard problem for human brains. But if we cranked at it for 500 years, we probably could do it. Or maybe even humans aren't smart enough to do it, but like, we have kind of reasons in principle for suspecting that it could be done.
I think I just find it hard to say anything one way or the other without looking at those specific reasons why we think that it's going to work out. I think everything depends on those specific reasons.
Good. Yeah. Right. Now, this gets, though, to the question of like whether motivationalism is really as radical as you kind of suggest in that statement of it, right? Because like, if it is, then I think the response for you to give would be, doesn't matter the details. If we don't have a construction, we're not licensed in drawing these conclusions yet.
I mean, you might, yeah. I mean, I kind of want to stick to my guns on that. You might make conjectures that you can regard them as they represent the same physical state of affairs or that kind of thing. But in the absence of the construction, I think you're not licensed in drawing that conclusion. I guess like Niels and I were chatting about this a bit before. I mean, I'm not sure I'm happy with describing motivationalism as radical, though. It's like I'm a conservative philosopher. I feel like it's a very conservative thesis.
Yeah, I mean, so when I say it's radical, obviously I'm being a bit provocative there, and but what seems a bit radical to me about it, I mean, I guess like maybe this kind of maybe the issue here is kind of like a bit of idealization that's going on in the terms of the discussion, right? Because like typically when we talk about interpreting physics, we say something like, I accept this interpretation. Like, this is my interpretation, like, of quantum mechanics. Like, let's say like I'm an Everettian or I'm a Bohmian. Like, this is my interpretation. Probably the reasonable thing to do is have like different degrees of belief in different interpretations, right? And then the question is, like, in a way, this kind of harkens back to what you were just saying, Niels. Like, Occam's razor isn't proof positive that the surplus structure is structure that doesn't exist. It's just kind of like maybe some reason to believe that the surplus structure doesn't exist, right? So it's like if you imagine that Newton's mechanics was 100% empirically reliable, then I guess like the position I would kind of take is, well, probably space and time have a Galilean structure. Maybe like 85%, like chance that they have a Galilean structure. Yeah, for like 5% chance that Newton was right and there's an absolute state of rest. Maybe something like that would be reasonable, right? And I guess I kind of feel like once you're looking at interpretation in that kind of more hedged or like, credence degrees of belief kind of way, then I kind of wonder what motivationalism looks like from that perspective, as opposed to from the perspective of like, when are you licensed in saying this is my interpretation 100%, right? Does that make sense?
I think I find this idea interesting, but it still feels like this kind of confirms the spirit of motivationalism in that, so the strongest form of the interpretational approach is not what Dewar does, but the strongest form is this, says you have a symmetry, you don't need to think anymore, you don't need to do any work, you need to do nothing. You know that it's just a difference of representation. And Dewar, of course, does more. He says, no, I have a tool and I have reason to think that tool always works, and this then supports the claim that interpretation always works. So, but if you now, for every specific case, need to check, okay, maybe in the future theories you mentioned, you have this and this reason to believe that this specific construction is going to work. And in Newton's case, it isn't. That's already giving up on the laziness of the strongest type of interpretationalism. So I guess I'm not really against the idea that in some cases you might have good reason to believe, well, it's very likely for some physical reasons, some conceptual reasons, or you think it's, well, a computational problem and in 20 years the computer is going to catch up. Yeah, in those cases that might work. But again, what we also try to point out in the paper, the main thing is it's not about whether we think, right, Dewar gives a few examples of sophistication. Even if they all work, that doesn't matter. The whole point is it needs to work universally, right? So any finite number is not really gonna get us all the way. So yeah, if there might be a few examples where you think, oh, Newton has 90 credence of 90% that this is gonna work, sure. But I mean, the bar, what we're trying to point out, the bar is very high for interpretationism, right? It needs to always work, needs to be guaranteed. So sure, we can maybe have some credence views, etc. I feel that's already kind of moving away from the laziness and the universalism. It's really a strong view interpretationism, which is not often knowledge.
Good. Yeah, I agree with that. Like, so I guess maybe like the thing I was thinking is that like interpretationalism is a really strong view. Like motivationalism, the way it's usually stated, also seems like a really strong view. And like in between those is a lot of space for intermediary views that say, well, like if you have a symmetry and you haven't constructed a manifestly invariant version of the theory that you're talking about, well, maybe there's other questions you need to answer in order to answer the question of whether you're licensed in treating symmetry related states as equivalent, right? Like you don't just need to answer, have I constructed a manifestly invariant version of the theory? You also need to say like, well, like to use my example, right? How likely do I think it is that a manifestly invariant version of the theory exists? Of course, we should ask like, how likely is it that if it exists, it's any good, because we could run into these kind of problems like what James was talking about before, where, maybe you come up with a manifestly invariant theory, but it's kind of gibberish. And you're like, I don't know how I can make physical sense of this, whereas I can make physical sense of the theory that isn't invariant that I started out with, right? So I guess maybe like my plea to you as motivationalists is to think, well, like maybe there's this kind of middle ground where like other considerations aside from do I have an invariant formalism in play, can kind of count in favor of like being an interpretationalist in this one case, but not an interpretationalist about everything the way that Dewar is or something.
Yeah, I also think that's super interesting, and I'm not necessarily opposed to it at all. So I think exploring this like middle ground idea of like incorporating degrees of belief and consideration of other factors into the interpretational, motivational axis is a good idea.
So what you just said at the end, right? You can be interpretationalist in some cases and not in others. I'm not sure I like the rest of what you said, but that seems, again, it seems to me interpretationalism.
Oh yeah, I guess
let me say it another way.
Yeah.
I think although you just nuanced what we do in the paper, I do think we were, to some extent, we haven't yet talked about this here, but to some extent we are trying to be sensitive to this in the paper, in that we propose a spectrum of views, which we haven't yet talked about, so let me introduce it. Right, on the one end, you have what we call the strong interpretationalism, and then the other end, you have the strong motivationalism, and then here you have weak interpretationalism, and here weak motivationalism. What do we mean by that? The strong interpretationalist says, doesn't matter, this is the laziest view. Say always symmetry related models. You don't need anything. You don't need an underlying common ontology. You can always make the metaphysical claim you want to make. Then the weak interpretationalism says, okay, we don't need to wait on, we don't need to search for metaphysically perspicuous characterization, but there can be extra empirical or explanatory reasons to think we should not want a theory that, we don't want to make the metaphysical move of saying symmetry-related models represent the same state of affairs, because you might lose out on explanatory power. And then you can kind of make the same distinction on the motivationist aspect, where the weak motivationist, which we take to be Tom Nielsen, says you need metaphysically perspicuous characterization. As soon as you have that, yes, you can make the move to say symmetry-related models represent the same state of affairs. But you can go stronger, which is my view, say, well, there's one other thing that can block that metaphysical inference. You need to check that you have a metaphysically perspicuous characterization, and you need to make sure that it doesn't lead to a loss in explanatory extra empirical power. And I think the nuance you added is, yes, you can have more of a spectrum there, where you can also add the kind of have a credence versions of these. So you can say, if there are other reasons to ensure that there's a high credence, to give you a high credence, that either an explanatory metaphysically perspicuous version underlying ontology is going to be found, or that such a thing will not lead to a reduction in explanatory power, yeah, then you could I think it would be good to add that to that spectrum of views.
Yeah, good, because like a thing that I totally am on board with about your view is that, for example, like if if the angel of the Lord came down and said there is no metaphysically perspicuous version of a theory that's totally invariant under this symmetry, like I think it would be bizarre to then say, yes, but I think that states related by this symmetry are physically equivalent. Like that, like if I knew that there was no satisfactory theory that was totally invariant in some sense, whether you think that internal sophistication is satisfactory for that, or whether you think no, I need reduction or something, like regardless, if you think there's no kind of like invariant theory in that sense, like it just seems to me like it would be bizarre to say, yeah, but even so, I'm an interpretationalist about this, right? So in that sense, like I'm totally on board with the spirit of what you're saying here. Yeah, good. I mean, there's a cool discussion. I don't know if you have anything else you wanted to kind of like add on. Yeah.
I'm just wondering, what are the senses in which we disagree, Dave? I mean, I don't.
Well, I mean, so the sense is like, so about the question, do I need to have a metaphysically perspicuous version of the theory in hand? I don't think you do need that. I think
reasons I just talked about.
Yeah, exactly. Like I think you can be justified in believing that one exists, even if you haven't constructed it. Right.
But it's a function of context, and
yeah, like there's a like, and I mean, to be clear, right, like I think the epistemology of this is super hard. Like, what is the epistemology of mathematical conjectures? Like, whoa, like I have no idea like what makes a mathematical conjecture justified. But like, I have a strong feeling that some of them are, you know, I mean, like, it would be weird if they weren't, right? You know, I think there's a huge amount of like unexplored territory here that's like really, you know, maybe we'll figure it out in 1,000 years or something, but it seems like a lot of really hard problems here.
Yeah, completely agree. But yeah, super interesting avenues for pursuit here as well.
Cool. Yeah, so one of the things that I wanted to ask about, I want to make sure to ask about, is kind of like the role of isomorphisms in the views that you're kind of like, well, I mean, actually, maybe in the interest of time, I'll skip this because I know we're a little bit time constrained, and I, at least let me save this for later, perhaps, because I want to make sure to get to the like actual, you know, one-on-one of you versus doer, right? Which we've talked a bit about, but like, so maybe what we should do is look at one of his examples and get to the question of why you think it's really not showing what he thinks it's showing, right? So like, we've been talking about electromagnetism, so maybe it would be instructive to kind of go over this with the case of electromagnetism and, you know, fiber bundles, which has already been on the table, right? So do you want to kind of go into how does Dewar use that example, and how is he kind of, according to the two of you, misconceiving the way that example, you know, the role that it plays in his argument for sophistication?
Well, I think we kind of covered it already. So Dewar is trying, at least as we read him, to argue for external sophistication. And he has 3 examples, and we can talk about, I don't know if we want to talk about those other ones as well. So one is like handedness, and one of them is electrostatics, I think. And then there's this full electrodynamics thing, which we talked about a bit already. And he says, by moving to the fiber bundle formalism of electromagnetism, I move to a formalism in which my models in the A theory formalism of electromagnetism, which were originally not isomorphic, actually are isomorphic now. I don't know if we want to go into the details of the fiber bundle construction or not.
Well, no. So I guess the thing that seems to be the crux of the disagreement, and yeah, maybe we did talk, but so the thing that seems to be the crux of the disagreement between you is that he sees the movement to the fiber bundle formalism as a case of external sophistication, whereas like, if I'm reading you two right, you say, well, hold on, like, if you really understand this case the right way, it's internal sophistication and not external sophistication. And like, the thing that would be external sophistication would be just throw out the version of the theory in terms of the potentials and don't say anything more, but just say like theories with gauge equivalent potentials, or rather states with gauge equivalent potentials are equivalent, period. I don't need to talk about fiber bundles, right?
Maybe one way of saying it is just like, you could maybe say that all cases of internal sophistication are like trivially cases of external sophistication, because you've done the hard work and provided the construction according to which the models are isomorphic. And then of course you can declare the models to be isomorphic and then apply traditional sophistication. And so in that trivial sense, I guess it is a case of external sophistication, but he's actually done internal sophistication as well. And what we're interested in is a case of external sophistication without internal sophistication. And I don't think that he gives us that in the article.
Yeah, what we tried to emphasize earlier is that it's very important to, except for this trivial sense, to point out that internal sophistication, external one, are really, is not the specific instance of the other, except for in this trivial sense, but they're really 2 distinct generalizations of traditional sophistication. And why is that important? Because in a way, internal sophistication is actually closer to reduction than either of these 2 are to external sophistication, in the sense that, remember, so reduction is do mathematical work, namely change the syntax, you're done. Internal sophistication is do mathematical work, not the syntax, because then it's reduction, but change the semantics, change the models. After that, you still need to make a metaphysical move, traditional sophistication. And then external sophistication is step 1, declare that they're isomorphic, doesn't matter if they are not, just stipulate it, and then make, again, this metaphysical move. Motivationalism is all about, do we need to do non-trivial work, and is it guaranteed that that work is going to be successful? And in that sense, reduction and internal sophistication are very similar, right? In that sense, we think they naturally pair, actually. So that relates to what you were saying earlier about which positions naturally pair with the other positions. In that sense, actually, internal sophistication very naturally pairs with motivationalism, because that's all about, do we need to do work before we can make the bold claim that symmetry related models represent the same state of affairs? And so in the electromagnetism case, what's going on there is there's first the move from the vector potential formulation to the fiber bundle formulation. That's very highly non-trivial, right? That's a big matter, and that's already, I mean, it doesn't even matter what you do after that. That's, I would say, motivationalism has won the game. This is only going to work if you do this highly non-trivial move. I don't see this why this was guaranteed at all that you're going to find this. So that's, I guess, the difference. Yeah, that's what's
no, that's good. And I guess that does kind of bring us actually to the question that I was thinking of asking just a minute ago, right? Which is like, what is it that's so important about isomorphism in the sense that, like, you know, so I mean, I guess, like, kind of like, let me say something that's a little bit hard to pin down maybe, but is kind of like a idea that I sometimes have about the way that mathematics gets used in interpreting physics, which is like, you know, which solutions are isomorphic to which. I mean, it's kind of something that we like decide almost by stipulation, right? It's like, you know, we're working with, you know, we're talking about this theory in this formalism rather than this other formalism, right? I guess I'll put it this way, you know, like when differential geometry was put forward in the first place, you know, like somebody like, you know, Gauss or somebody decided we're going to treat manifolds that you know, have the same differential structure as equivalent, even if they're not isomorphic as sets, right? So there's kind of like, there's two notions of isomorphism. There's isomorphism as sets, there's isomorphism as, you know, differentiable manifolds, right? And it's like which of those is really isomorphism, if that makes sense, right? Like so it's like I take two solutions of electricity magnetism. Well, they're isomorphic as like fiber bundle states, but not isomorphic as potential states. It's like, well, you know, it's like, yeah, what again, this is kind of like a fuzzy way of putting what I'm saying, but like, what's so important about isomorphism? Like, why do we say everything's kosher in regarding these as equivalent when we have an isomorphism, but not when we don't? When, like, what counts as an isomorphism is this thing that kind of gets stipulated by the mathematicians when they're coming up with the math that later gets used in describing the theory.
Yeah, so I agree, this is a super delicate business. I think when we talk about isomorphisms in these debates, we're often meaning like other models related by diffeomorphisms. So just think about the whole diffeomorphism in general relativity, where you're just like smushing around fields on the manifold again, and then you're falling into our first camp of symmetry. So you're changing which points, if you're a hexatheist, have which properties, and then the natural move to avoid regarding those models as representing distinct states of affairs is to be an anti-hexatheist, a sophisticated substantivalist. And the same in the case of the static shift. I do a diffeomorphism and I've shoved stuff 5 meters to the left. I can not regard those models as representing the same, regard those models as representing the same physical state of affairs if I'm an anti-hexatheist. Things become a bit more delicate in the case of the other kinds of transformations that we talk about, and we go into this in the paper. So think about like a kinematic shift. Like can that be construed as just the same kind of transformation? Well, no, because these uniform velocity boosts don't preserve that sigma field which represents the persisting points of Newtonian absolute space. So it's not the case that I can like d-star all of the elements of my model and regard the models as actually being related by a different. So that's how we explain it in the paper. And so you can't regard these models as just like moving stuff around on the manifold and so falling into our first class of transformation. So I think, I don't know if this is
in the case where
not,
Newtonian space is the background structure and not Galilean space-time, right?
Yeah, exactly. So we're thinking about like, you know, our usual objects for those who read the paper, like M, H, T, nabla, and then this problematic thing, sigma. And when I do my diffeomorphism, which moves my material fields, which are the matter density field and the gravitational potential, what I want to do is I want to ask myself, can I like, when I do that transformation, is it the case that my like H is equal to D star H and my T is equal to D star T? And for some of them, it's true. Those transformations do preserve like the spatial metric or the temporal metric, but the transformations do not preserve this field sigma. And so I can't, once I've gone to like D-starring my material fields, D-star everything and regard these guys as being related by a diffeomorphism, and then regard these guys as falling into the first camp of just differing with respect to where stuff is on the manifold. So I think implicitly, and I agree, this is like a point of kind of unclarity in the literature. What people are meaning by isomorphism is something like this. But of course, there are other notions of isomorphism as well. But I think this is what people mean. I don't know if that's helpful or not.
Yeah, that's helpful. And so then, like, I guess the other part of the question is, what makes that notion of isomorphism kind of the crux of the question, right? What is it that, you know, why is it that when we have that sort of an isomorphism, we have a satisfactory understanding of, you know, a perspicuous understanding of how the states could be equivalent, whereas when we don't have it, we don't have a perspicuous understanding?
I guess I would say that because that's the notion of isomorphism, where when I interpret the models, they seem to represent possible worlds which differ merely with respect to where things are on the manifold. And so that's the notion of isomorphism, which is amenable to sophisticated substantivalism as a strategy for, in fact, regarding these models as representing the same possible world. And you could have some other fancier notion of isomorphism, but it might not necessarily be one which is amenable to the sophisticated substantivalist anti-Hexiatist move.
Yeah, good. So like I think the phrase used in the paper is, you can interpret models related by that kind of symmetry as being merely qualitatively different.
Yeah.
You know, or actually the other way around, like merely identity-wise different, but not qualitatively different.
Mm-hmm.
Right.
Yeah.
Yeah, good. Good. Yeah. Yeah, I think like, and I think there are kind of, I guess in some ways, kind of like parallels of some of the things that have come up kind of arise in this regard, like in the sense of like, one could say, well, maybe I could put forward a theory where I'm kind of talking about two types of qualitative structure and say my interpretation of the theory is that I'm a realist about one of them, but not about the other, right? So like, for example, I could put forward a formulation of the theory in terms of, you know, in the electromagnetism case, I could put forward a formulation in terms of the vector potential and like the field tensor. And I could say like, well, I only think one of these two things is real, right? Even though like the formalism is talking about both of them, like one of them is the one that I think is real and the other one is the one that I think isn't real. Like I think the field tensor is real maybe, and I don't think that the potential is real, right? Now is that an unsatisfactory move on your view?
I think no. I think think it's fine in this case because we have like a clear idea of how to construct a Faraday tensor from a 4-vector potential, say. So it doesn't seem like I need to ontologically commit myself to both. Like, I can write both in my models if I want, but I also have a pretty straightforward story about how one is derivative on the other.
And in that
Still,
sense, like, yeah.
Am I tracking the question?
Oh, well, yeah. I mean, so maybe the sense is that maybe what you're saying is like I can't put forward a theory that has both the potential and the field tensor without also realizing that a reduced theory, in the sense that it only talks about the field tensor and not the potential, is also, you know, straightforwardly constructible from that, right? Is that the idea? Like it's like the theory in terms of the potential also kind of like contains as a substructure a sort of reduced theory in terms of the field tensor. And so like, yeah, just saying like, I believe that reduced theory is okay.
But maybe I think that's right. But maybe I would just stress in addition that we seem to be thinking about things just in terms of like the mathematical objects in a model. But I think we should also pay attention to like the dynamics that they obey, because maybe this A field obeys some completely non-electrodynamic equations which are nothing to do with F, and then this reduction would not be appropriate. It's only when we have like the standard Maxwell equations that we can,
yeah,
that we can understand how we can do without one of these guys.
Cool. No, that makes sense. Okay. Yeah, I mean, this is great. So this discussion has given me a really kind of like I think richer picture of how all the parts of the view hang together. And there are a lot of parts of the view, and like there's a lot of, I mean, I just like, you know, one of the things that I love about what you're doing is that it's really rock bottom, right? Like a lot of what you're doing is kind of like, I mean, in a way, like the kind of like foundational work that I feel like philosophy of physics has been kind of like lacking and in need of for a long time. Like, I think that one of the things philosophers of physics don't do very much is say, like, here's what we're doing, here's what we're talking about when we talk about philosophy of physics, right? Like a lot of areas of philosophy have more kind of meta theory, we might say, than philosophy of physics does. So one of the things that I think is cool about what you're doing is that it's kind of like providing some of that foundation for philosophy of physics. You know, and of course, like hat tip as always to Muller Nielsen, who kind of started us down this road, which I think has been, you know, it's like, yeah, like I think this like direction of inquiry has been really beneficial to the field so far, and like I hope will kind of continue to pay dividends. So I have these kind of questions that I like to end with, right? I guess maybe I should change the first one, because like the problem with the first one is that oftentimes it kind of like comes up in the discussion. But like, you know, the first one that I often ask is like, you know, have there been any changes in the way that you think of the subject matter of this essay and the time since you published it? And, you know, I guess, you know, maybe we've kind of touched on bits of that, but like, is there anything along those lines that we haven't touched on already in this discussion?
Yeah, so we're thinking of maybe writing a sequel paper, indeed. And I think what we've been doing in this paper is, to some extent, having a discussion on doers' terms. And I think we might want to move a bit beyond that. So one thing, one question to ask is that it seems to be the case that there are several ways of defining the difference between reduction and sophistication, and it's clear that they always line up. So one way of saying one way is saying, well, you either modify the syntax, that's reduction, or you modify the semantics. That's one way of putting it. Another way of putting it is, in the case of reduction, you go from a plurality of models to a single model, whereas in the case of sophistication, you keep the same amount of models, but you just to specify their isomorphic and kind of modify their mapping to the real world. And it's not clear to us that it's always that those definitions are coextensive. And perhaps relates to that is that we've now, I think, up to the Dewar's paper and our paper, we're kind of I think have implicitly all agreed that there's always, if you make a mathematical move, that it's always clear that's going to be it has to be either reduction or a sophistication, and it can be both at the same time. But it seems like in some instances of sophistication, it's kind of piggyback on reductionism, and it's basically reductionism in disguise, or at least that it's not really clear what's going on there. So, for instance, we tend to say, and I think we said it in the paper, that the move to Galilean spacetime is one of reduction, and like Neil Dewar and maybe Caspar Jacobs at times think, no, that's actually into sophistication. So maybe we're both right, or maybe we're just doing different things, starting from different theories. But one way of looking at what's going on there is, sure, if you start with a standard Newtonian spacetime on standard Newtonian gravity Newtonian spacetime, where you have identity of spacetime points over time, and then you define your absolute velocities in terms of that, and relative velocity in terms of that, etc. You can reduce that theory, right? That's your original theory. You can reduce that and go to Galilean spacetime. But you can then also use that to create an alternative initial theory by adding to the Galilean spacetime. You just say, well, Galilean spacetime only tells you if time-like curves are straight or not. It doesn't give you an absolute velocity, but you could just have a theory that is Galilean spacetime plus picking out one of these straight line in kind of quiddatistic way and saying, well, that one is going to be the absolute velocity, right? So then you have a theory here, which is this theory, but you add some quiddatistic property, right? And then you can say, oh, well, if you then start out with this theory, and then all you need to do is forget that quiddatistic property, and you have a right at Galilean spacetime. So now it seems, the move to Galilean spacetime is sophistication, whereas we had said here, well, the move from this theory to Galilean spacetime is reduction. So it kind of seems you can always, the sophisticate can always piggyback on a reductionist by kind of adding this extra little, adding this label, this quiddatistic or hexatistic property, and forgetting it. So that seems to be kind of piggybacking on it. And that, of course, only works if you think this is the traditional original theory of Newtonian physics to start with, and then you can make that move. But if you want to couple sophistication to invitationalism, it needs to work for all theories, not what you have chosen as your idiosyncratic way of saying, well, this is standard Newtonian physics, and their sophistication is going to work, right? It always needs to work. So
in Niels' paper, which, by the way, we both think is great, he does articulate a whole bunch of different, or several different ways in which you might understand the reduction sophistication distinction, like Niels was mentioning. And I, throughout this, I think Niels as well mostly was thinking about it in terms of forgetting structure to keep the same number of models such that the models are now isomorphic. And just to say, having chatted with Neil about this a fair bit, I'm pretty confident, you can correct us if I'm wrong, but I'm pretty confident he thinks that this is the best way of understanding the distinction on reflection. Like, obviously he was trying to introduce something new in that paper, so it's not surprising that he was trying to get at it in different ways. But I think that would be his settled view on the understanding of the distinction, and that's how at least I tend to talk about it now. But yeah, it's still worth, I think, doing what Niels was saying and showing how these different ways of understanding the distinction in fact don't line up.
Yeah, cool. That is really interesting if they don't. That's actually a possibility that I had not envisaged, but it makes sense that it would be. Very cool. Okay, well, that's awesome. Second kind of ending question is, what's something that you're working on? I guess we just heard about one thing that you're working on but do you have anything that's kind of out now, or that you're kind of finishing up that you'd like our viewers and listeners to know about?
I'll say something which is related to this, which I'm quite excited about. So one person that we've mentioned is Caspar Jacobs, and there's this long-standing issue of whether gravitational energy makes sense in general relativity. You seem to have a whole bunch of different candidate objects which could represent it, so-called gravitational stress energy pseudotensors. What Brian Pitts does is say, I can make sense of gravitational energy by kind of taking the union of all of these, and that's become known in the community as a Pittsified object, which somehow is supposed to represent gravitational energy. But Caspar and I think this is kind of in some way which we're aiming to make precise, like external sophistication. He's kind of like bundled up all of the stuff together, but he hasn't really given us like an intrinsic characterization of what's going on here. So what Casper and I are trying to do is trying to like define something which would be naturally related to the Pitts object, and that's like ends up being some differential forms on some fiber bundle or something. So I think just to say that this distinction, I think, has the potential to be fruitful and to further the debate in other areas of the philosophy of space-time and the philosophy of physics more generally. So that's something that I'm working with Casper now, which I'm kind of excited about.
Yeah, I mean, if you can put forward a view about like what is the gravitational energy, that's pretty big progress on a tough question. So that would be really cool, James. What about you, Niels?
Yeah, it depends a bit on whether it's supposed to be work that's somewhat related to this paper or whether it can be.
Not necessarily. I mean, you're working on a book now, right?
Yeah. Oh, yeah. Maybe I can say a bit of both. Yeah. So stuff that's roughly related to this kind of stuff is two things. One is a paper, which I mean, yeah, a full manuscript, which is what we do refer to in our paper, which basically tells the story of what I said about Occam's razor and uses the Aharonov-Bohm effect as a case study to illustrate that, which I really should. It's kind of almost done, so I should just get this out. And indeed, a book in the Element series with CUP on the philosophy of physical quantities, which talks about absolutist, comparativist views, which of course you have worked on yourself. And that's hopefully going to come out towards the end of this year. And then there's kind of a whole area which doesn't have anything to do with this, stuff about dark matter, black holes, dark energy. Maybe the most interesting thing right now to mention there is that as part of the Next Generation Event Horizon Telescope collaboration, this is a collaboration which is going to make the first video of black holes. They're including historians and philosophers and sociologists, etc., scholars from the humanities and social sciences, right from the start as one of the 8 working groups, which I think is pretty cool to be directly engaged with the scientific collaboration of quite a large size. So we're working on a white paper there as how can we contribute in real time as philosophers, historians, etc., to astronomy, to physics. So that's what I'm quite excited about right now.
Pretty sweet. So with the quantities book, how much of the material, I mean, I guess this probably isn't fully settled yet, but how much of the material from your dissertation do you think you'll be able to fit into it? Because that's like, there's a lot of great stuff in that dissertation.
Thanks. Yeah, quite a fair bit, actually. I do want to add also a few additional or a few different bits. One of those would be sophisticated absolutism, which is a view that Casper Jacobs likes. So discussion of that. And I think very recent is more discussion on what constants of nature mean, because usually we talk about quantities and should it be quantitative, should it be comparative, absolute. But often these debates where we talk about symmetries, when we scale stuff, kind of an implicit question is, okay, when we scale, when we do shifts, scale masses, etc., what happens to constants of nature, like G, right? And some people, like Casper Jacobs, think you should scale them along. And I tend to think, no, the game we should be playing is, if you want to know how to do the metaphysics of masses, then keep everything else the same, which includes the G, which represents or parameterizes the strength of the force, and then see if something observational changes or not when you scale masses. Yeah, so that's, yeah.
You and I are of one mind on this question. All right, very cool. Wonderful to see you too. Like wonderful to talk about this great paper, and I hope viewers enjoyed as much as I did.
Thanks so much, Dave. That was really enjoyable and illuminating.
Yes, thanks for inviting us. It was fun.
Of course.